In this particular presentation, we're going to talk about the method of separation of variables for the heat equation. And this method is a neat way of solving many simple PDEs, many linear PDEs that we'll come across in this course. Now, we'll also discuss the need for Fourier series. Some PDEs, some boundary value problems associated with them only really require the separation of variables method. They don't really need Fourier series. But in other cases, you do need Fourier series. Okay, so what we're going to concentrate is on the method of separation of variables, and then use Fourier series or show you the need for Fourier series at the end. Now, in this course, we haven't learnt Fourier series yet, so we're not going to spend too much time on it, but we will show you the need for Fourier series. Okay, so the method is called the method of separation of variables, and like I said, it can be used to solve lots of simple linear PDEs. And to give some sort of concreteness, we're going to solve the following problem. So you can see that the first equation, equation 3, is just a specific example of the heat equation that I've derived in the previous class with alpha squared equals 4. You can also see that the length of the bar would be pi units. Now that's a little bit cute, right? Make me a bar of pi unit length. I dare you. Okay, so this is just, the pi here is just for simplicity. Okay? Now, there's some other conditions as well. So-called boundary conditions on the ends of the bar. These two conditions say that at the left-hand endpoint, the temperature is maintained to be 0, and at the right-hand endpoint, the temperature is also 0. And this is for all positive time. And then finally, down here, we've got something like an initial temperature. So when time equals 0, the bar has some sort of temperature associated with it, given by this f of x. Now, I'm not going to tell you what f of x is. Okay, it'll be some given function, but as we'll see, the structure of the initial temperature function, f of x, plays a huge role at the end of this method. Okay? So, we have a PDE, some boundary conditions, and what I like to call an initial temperature condition, whose precise form will be discussed a little bit later. Okay, so if I wanted to sort of draw a little picture here, you've got your bar, that's lying along, say, the x-axis. And we assume that our bar's thin, so if you look at the cross-section, say that shaded cross-section, it's a function of x only and time. Okay? Now, this is a nice picture because it kind of gives you some physical understanding of the bar, but you can also draw these conditions in the xt plane. All right? So here, this is when x equals 0. Well, it's just this axis here. So along this line, this tells us that the temperature is 0. When x equals pi, and for all t, this condition tells us the temperature is also 0 along that line. Now, the condition 6, that's when t equals 0. But x is between 0 and big, sorry, let me adjust that. That L should be pi. Okay. Our temperature along this edge, if you like, is f of x. Okay, and inside everything, our PDE holds. Okay? So the question is, how do we solve it? Well, in the previous lecture, I did show you a very quick solution, the sort of general form here, provided f could be written in this form. So where does this form come from? That's what we're going to talk about. Okay, the fundamental step with separation of variables is you assume the solution is just the product of two functions, and each of those functions depend on one variable only. So big X times little x, big X of x times big T of little t. Okay, that boxed expression is a fundamental part of the solution here. So what we do then is we try this form and then suitably adjust the form by incorporating the various conditions associated with our heat problem. Now, if we look back to the original solution that I showed you in the previous lecture, right? If I just cover that up, it's a function of t times a function of x, and you're summing over the ends here. Okay? But that's a lot more complicated than this idea here. So we're going to start simply and then progressively get more complex. Okay, so the first idea is to look at your PDE, and you can see I've got u sub xx and u sub t. What I want to do then is take this form and calculate these particular derivatives. Okay, so let's call this star. All right, so we want u sub xx and u sub t. Now, u sub x, well, let's differentiate this partially with respect to little x. Because I've got a product of two functions of separate variables, it's just the following. Okay, where by the dash I mean just regular differentiation with respect to the independent variable. Okay, so u sub xx, what's that going to be? Well, it's just going to be x double prime times big X double prime times big T. Okay. U sub t, well, that's going to be, just differentiate this partially with respect to little t. Okay. So now we take these two expressions and sub them into our original PDE. Okay. Okay, our PDE3 is going to come from the following. This is going to go to 4 x, big X double prime of x times big T of t equals this. The crucial stage. Can I rearrange that equation and separate the variables? Okay. Well, if I take big X of x, say, over to the left, and say 4 times big T of t over to the right, I can use division to separate the variables. Okay, so we're going to form something like this. Now this is a good place to be because I've been able to separate the variables. You can't always do this with every PDE. Okay, but if you can get to this stage, you're pretty confident that the method of separation of variables will work. Okay? All right. Now I'm going to make the following claim. The two ratios we have here are equal to a constant, say gamma. Now, how can I justify that these things are equal to a constant? Well, look on the left-hand side. Okay, just forget about this for a second. If I vary little x, you would expect the left-hand side to vary, right? Okay? But these two things are equal, and there's no x's over here. So if I vary that side, that's got to stay the same. If I look over here, the variable's little t. If I vary that, well, we would expect this to vary, but there's no little t's over here. So it's got to stay the same. So the only expression, the only explanation for that is that these ratios have got to be equal to a constant. Okay? That's the only explanation. Okay? So I'll introduce this a little bit later, but that's, I mean, you can keep that there if you want. So let me just write that out in words. Since the left-hand side of double star only depends on x, and since the right-hand side of double star only depends on t, we must have a constant, say gamma, okay. Now that boxed expression down the bottom is actually what we're going to work with. We're going to form two ODEs out of that boxed expression. And then we're going to solve them. And we're going to determine what kind of values our constant gamma, called the separation constant, what kind of values of this gamma give a non-trivial or non-zero, if you like, solution to our problem. Okay. So, just from this expression, we can form two ODEs. So, forget about that. I can bring this up here and form an ODE for big X. And then forget about that. I can form an ODE from that in big T. So you might want to, draw a line down the center of the page here or something like that, because there's a lot to write. Okay, so let's just take the order one. So if I rearrange that, I'm going to get something like this. And I'm going to get a second order one as well. And I'll write it this way. Okay, so if we can solve those two ODEs, then I think we're on our way to getting the solution to our original problem, because theoretically all we would do is multiply the two things together. Okay, well, let's solve this first one. Okay, does it look familiar? It was in everyone's class test this week. We can just write down the answer. It's some sort of exponential function, right? So let me just say c is a constant here. So it's some sort of exponential function where c is a constant. And what about this one? Well, this is a second order linear ODE with constant coefficients. The ODE down the bottom is a second order linear ODE, right? So gamma is just a constant. So how do we usually solve these problems? Well, we write down we can solve them a bunch of ways. But for this one, the easiest way is just to write down the characteristic equation. Okay? So the characteristic equation, let's say in terms of lambda, it'll be lambda squared minus gamma. So it's just this. Okay. So depending on the sign of this separation constant, gamma, I'll either get real and unequal lambdas, I'll get complex lambdas, or if, say, gamma is 0, I'll just, if the gamma is 0, I can solve this straight away because I'll get that. Okay, so we're going to discuss those cases and build the following. Okay, so the simplest case is when gamma is 0. If gamma is 0, then I can integrate this twice, right? Just directly. I can integrate this twice to get the following solution. Right. Now, what about, say, when gamma is positive? When gamma is positive, our characteristic equation will have real and unequal roots, just plus root gamma and minus root gamma. In this case, the solution would be the following. So they're real and unequal. Okay? And we've spent a lot of time in class solving these kinds of basic ODEs. Now the third case is where gamma is negative. Now when gamma is negative, what kind of roots are we going to get here? Complex roots, right? So in that case, we're going to have sines and cosines in our solution. Okay, so now this might look a bit weird because I've got a negative gamma, but remember gamma is negative in here, so this will be the square root of something positive in here. So in this case, the roots are complex. Okay? So there are three potential solutions that we're going to try to work with. Okay? So the functions of interest now are this, and of course this big X here. Okay. So now what we're going to do is try to find which one of the forms is appropriate. To do that, what we're going to do is look at the values of this separation constant gamma that give non-trivial solutions. In other words, non-zero solutions. How do we do that? Well, we look at these two boundary conditions, 4 and 5. We haven't used them yet. So the only thing we've been working with up until now is the original PDE. Now it's time to introduce these conditions here, and then later on we'll work with this. Okay, so the idea now is to introduce the boundary conditions 4 and 5. And we determine which values of our separation constant, gamma, lead to non-trivial. When I say non-trivial, I mean they're non-zero solutions. Okay, so here are our two conditions, and we've assumed that U is in a special form, right? It's the product of one function of x times another function of t. So we can actually use that to come up with some boundary condition for this particular function. Okay, let me show you what I mean. So the boundary conditions (4 and 5) yield the following. Well, the first one is this equals 0. But remember, because of our special form, this would correspond to that. So what do we know about big X of 0? It's got to be 0, right? The only other explanation is big T 0. But if big T is 0, what does that tell you about U? Well, it's got to be 0. It's got to be the trivial solution. So we'll ignore that case. So this second one gives us big X of pi equals 0. Okay, so we ignore, say, big T equals 0, since this produces the trivial solution. Okay. So these two boundary conditions can now be related back with these forms, and then we can see, all right, well, what kinds of this particular solution, big X, do we want that sort of line up with these two conditions? Okay. So let's discuss the cases separately. Let's discuss the case gamma equals 0 first. Well, what we do is we take this and apply these two boundary conditions to big X. Okay, so let's call this, yep, you guessed it, triple star. Okay, well, at the left-hand endpoint, little x equals 0, so big B is going to be 0. So that's big B is going to be 0. At the right-hand endpoint, we're going to get a of pi equals 0. So that means big A equals 0. So we've just formed a solution where AX plus B, where big A equals 0 and big B equals 0. So that's going to give us the trivial solution. But this yields the trivial solution. So what does that mean? It means that we can forget about this form and forget about this value of the separation constant. Okay? So let's now discuss this case where the separation constant's positive. Okay? Look at this and test it again on the same boundary conditions. So all right, well, at the left-hand endpoint, so we're going to get e to the 0 and e to the 0. We're going to get a plus b equals 0. So say a equals minus b, if you like. And at the right-hand endpoint, we're going to get a e to the root gamma pi plus b e to the root gamma to the minus root gamma pi equals 0. All right, we want to solve for the big A and big B. We've got two equations and two unknowns in that respect. So if you just sort of put this into the second equation, you can form the following. Okay, just a little bit of factorization. Minus. Okay, so just putting one into the other and doing a little bit of factorization, you can come up with the following. Now, that bottom line says either big A equals 0 or everything in the bracket 0. Now, let's just consider the first case. If big A equals 0, big B's also got to equal 0. So this will just give you the trivial solution, right? What about what's in the bracket? Well, what's in the bracket can never be 0 for positive gamma. Okay? It's impossible. Okay? So this again yields the trivial solution. Okay? The only way that what's in the brackets can be 0 is if gamma equals 0. But we're not discussing the case gamma equals 0. Okay, we're discussing the case when gamma is positive. So A has got to be 0. So what does it mean? It means that we can rule out this form. But the third form of the solution, it was just right. it turns out that this case is going to be the case of interest. Okay? So this is the business end now. The case when the separation constant is negative. So we'll take this form again and apply these boundary conditions, and then we'll produce some non-trivial solution, some non-zero solution. Okay? Okay, we're going to yield the following. Well, at the left-hand endpoint, little x equals 0. So that's going to be 0. Sign of 0 is 1. So well, this a has got to be 0. Okay? Uh-oh, doesn't look too good, but the other endpoint's going to give us something important. Sorry. Okay, well, if that a is 0, then we can cover that up. Plug in little x equals pi and set everything equal to 0. Okay, so now we've got something to work with. This bottom line means that the constant b is either 0, we don't want that because then we'll get another trivial solution, or sine is 0. So think about the sine function. When is the sine function 0? Well, it's 0 at pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. So we're going to consider this. Now the sine function is 0 at multiples of pi. Pi, 2 pi, 3 pi. That's where it crosses the axis. So if I write it like this, then I can cross off the pi's. And we're going to get some sort of non-trivial solution here. So you can see I've kind of got a sequence of solutions. So what it means is I can go back to this expression, the big A is 0, and I can replace root negative gamma with n. N equals 1, 2, 3, 4, etc. Okay? Now, for each of those values of n, we need a specific constant. So one value of b won't cut it. What I need is a sequence of constants. b1, b2, b3, b4. Okay? Okay, so what we have done now, we have formed a sequence of functions where the b sub n's are constants. Okay. So this is good. We're being constructive now. Okay, well, from this expression, I can come up with gamma, and then I can go back to this original function and replace gamma with, it's going to be something like minus n squared, something like that. Yeah, minus n squared. So it's a plus for gamma t. Okay, so I'm just going to replace the, so rearrange this, and I'll get gamma equals negative n squared, and essentially I can form, again, another sequence of functions. Where the Cn is just, again, the constants. Okay? Now, because our original PDE is linear and it has zero boundary conditions, I can use a rule called the law of superposition, which means, right, that say if I multiply these two things together, I can form a whole sequence of solutions or sequence of functions. That sum will also be a solution. So let's multiply these two things together, and then we'll sum them all up. Okay, so using this and this, I'm just going to multiply them together. Right? And then look at these two sort of sequence of constants. Let's just call their product, say, little b sub n. Just to sort of, so we have one fewer constant flying around. Okay? All right, we're almost there. Since our PDE is linear and the boundary conditions are, since our PDE is linear and homogeneous, it's got a zero, if you switch it around, it's got a zero right-hand side, and our boundary conditions are also homogeneous, they have a zero right-hand side, essentially what you can do is just sum up this sequence of functions and form some sort of general solution. So since our PDE and these associated boundary conditions are linear and homogeneous, every sum of solutions is also a solution. So hence, we can form the following. So I'm summing over the ends now. Okay. Now this form is a special case of the slide I put up right at the start, where I told you it was quite a strange looking sum. But a couple of things to consider. Firstly, I've got an infinite sum there, which is kind of dangerous sometimes, right? We don't know whether the sum is well defined or not. Okay? Secondly, how do I calculate? The only thing that's stopping us from getting the final solution here are these sequence of constants, b sub n. Well, what haven't I used yet? I've used the PDE and I've used these two conditions, but I haven't used 6 yet. Okay? Now to determine the constants, the b sub n, essentially what you do is you use the initial temperature, the condition that we haven't used yet. Okay? So what does this condition mean? Don't worry about f of x yet. If t equals 0, let's go to my sum here. Well, if t equals 0, this exponential is just going to become 1. Okay? So I've got a sum involving these b sub n's and the sine function. Now we're told that the initial temperature is some function of x. So what we would sort of have to assume here is that you can write f of x as an infinite sum involving sines. And this is where Fourier series come in. Okay, so the only thing stopping us from having a full solution here is finding the b sub n's. And to do that, we incorporate the initial temperature. So if we go up here and just plug in t equals 0, I'll get something like that. Now, what this is saying is that we're sort of making the assumption that we can, let's say f of x is like x squared, right? What that bottom line says is that I can write x squared as some infinite sum involving sines and b sub n's. Okay? So how to do it? How do you do it? Well, that's what Fourier series are all about. Now, some of these problems, you don't need Fourier series. Let me show you. Okay, so this is like our general form here. It's very sensitive to the initial temperature. Now, let's suppose your initial temperature was some finite sum of sine functions. So I'll give you an example. Suppose that your given initial temperature of your bar was this, sine x minus 2 sine 3x. Well, from this expression, what you could do is determine the b sub n's. You would just take this and compare and go, all right, well, b1's got to be 1, b2's got to be 0, b3's got to be minus 2, b4's got to be 0, b5's got to be 0, etc. Okay? So actually, if you have a suitable initial temperature, you don't need Fourier series. You can just compare the coefficients because you can write the initial temperature as a finite sum of appropriate sine functions. And then you just equate the coefficients. Okay? This infinite sum would just become this much simpler version because all the, except for 2, all the B sub, B sub 1 and B sub 3, the rest of the B sub n's are all 0. So you don't actually have an infinite sum. But what happens if you have an initial temperature like this, say the x function, right? Just to choose something simple. What you would have to do is write x as some infinite sum involving sine functions and B sub n's. So how do we do this? How do we write x as a sum of this? And how do I determine the B sub n's? Well, this is the exact question that Fourier asked himself way back. So he sat down and developed a way for writing functions in terms of sines and cosines as an infinite sum. It turns out that, as we'll see in later lectures, that the B sub n's here can be calculated from the following formula. Okay, so for this particular example, provided f of x satisfies certain conditions, so this x would satisfy those kind of conditions, you can produce the B sub n's using this integral. But this is, we'll learn about this more in Fourier series next week.